I now declare this frickin' idiot convention open!
The last topic that we'll study in the first section is the difference between angular speed and linear speed. If we look at a circle that's spun around its axis, where the axis is put through the center, we can keep track of how much the angle changes per unit time. That's called angular speed. Omega, curvy W, is the variable used to state angular speed, and by definition, angular speed is the change in angle, or delta theta, over the change in time. If you keep track of how much the angle changes for a certain amount of time, you'll be calculating the angular speed. Since we can look at points on a circle, as a point travels, it moves a certain distance. So the linear speed is a comparison of the change in distance over change in time. Since we normally call the distance that a point travels on a circle an arc, you also might see it as delta S over delta T. Well, since we have a definition that says S equals r theta, in other words, the arc length is equal to the radius times the angle that's cut off by the two radii, we can take and substitute r theta into our linear speed formula, and we find out that linear speed is the same thing as r theta over delta t. So as time changes, if we keep track of how much the angle changes, linear speed can be calculated as r times omega. So now we have three variables that can be measured when a circle is rotated around its center. The first is the angular speed. Second is the linear speed. And the third is the formula that connects the two. Linear speed is radius times the angular speed. We can compare linear and angular speed by looking at points traveling in a circle. Point D is inside a circle, point C is on a circle, and since the circle has a radius of 1, this is a unit circle. If I put both those points in motion, after a set amount of time, they both traveled the same angle theta. Since they've traveled the same angle in the same amount of time, both of their angular speeds are the same. In other words, omega for the blue is equal to omega for the red. Their linear speeds are different, however. The blue point was further out on the circle. It's on a circle with a larger radius than the red point here. So in the same amount of time, the blue had to travel a larger distance than the red. That means that their linear speeds are different, and that the linear speed for the blue is greater than linear speed for the red. CD players know this and have to take this into account. If you read this paragraph right here, when playing back music, a compact disc employs constant linear velocity to maintain a constant data rate. In other words, because the radius keeps increasing, the CD player has to keep changing the angular velocity so that the linear velocity remains constant. Our example will use a CD player that rotates at a constant 180 RPMs. RPM stands for revolutions per minute. The first thing we would need to do is take 180 RPMs, revolutions per minute, and convert that into radians per minute. Since one revolution around the circle is the same thing as one circumference, or 2 pi, we know that one revolution is the same thing as 2 pi radians. If I take and multiply 180 revolutions per minute times the conversion factor of 2 pi radians for every one revolution, revolutions will cancel out, and I'll get 360 pi radians per minute. Radians aren't really a unit, but I'm going to include them here so that we don't get lost in what we're doing. In order to calculate the angular speed, we know that the angular speed is change in angle over change in time. Since I just figured out that 360 pi radians per minute is a change in angle over a change in time, we already have that answer, 360 pi radians per minute. To calculate the linear speed, change in distance over change in time. The distance is the same thing as an arc length, which is r times theta. So to calculate the linear speed, I'm going to take our radius, 6 centimeters, multiply it by our angle, 360 pi, and divide that by time, which happens to be 1 minute. So linear speed is 6 times 360, 2160 pi per 1 minute, and units, even though 360 pi was measured in radians, we only keep the centimeters. If I were to convert that into a decimal, it's going to be roughly 6,785 centimeters per minute. The last example involves two spinning discs with a belt connecting both of them. We're told that the first disc has a radius of 15 centimeters, the second disc has a radius of 5 centimeters, and the first one has an angular velocity of 3,000 RPM. The first thing we need to do is convert radians per minute, or RPMs, into radians per minute. The conversion factor is 1 revolution, or 1 trip around the circle, is the same thing as 2 pi radians. So when we go to figure out the angular velocity in the correct units, the angular velocity on the first disk is change in angle over change in time. I've got 3,000 revolutions for every 1 minute, but revolutions is not an angle. When I multiply it by revolutions in the bottom and radians in the top, the revolutions will cancel, and I'll be left with radians per minute, which is a change in angle over a change in time. Again, the conversion factor is there are 2 pi radians for every 1 revolution. So the angular velocity on the first is 6,000 pi radians for every 1 minute. Now that I have an angular velocity in terms of change in angle over change in time, I can convert this into a linear velocity. Once I take the first angular velocity and convert it into a linear velocity, any point traveling on the belt is going to have the exact same speed. The belt always travels the same speed all the way around. So once I figure out the linear velocity on the first, that's going to be identical to the linear velocity on the second. Again, the conversion between velocities is linear velocity is radius times angular velocity. So I'm going to take the radius of the first, which is 15 centimeters, multiply by the angular velocity I just found, 6,000 pi radians per minute, and I'm going to get 90,000 pi. The units will become centimeters per minute because radians really isn't a unit and I don't need it anymore. So centimeters per minute. A change in distance over a change in time is the velocity. And again, since every point on the belt has to travel the same speed, that V1 is going to be put on the second disk, and now I can start working on the second disk. V1 is the same as V2, which has to equal 90,000 pi centimeters per minute. I need to convert this into an angular velocity. Again, I'll use my formula. V2 equals radius 2 times omega 2. I'm going to take 90,000 pi centimeters per minute and say that that equals 5 centimeters times the second angular velocity. When I divide both sides by 5, I wind up with that canceling. I wind up with an angular velocity of 90,000 pi divided by 5 is 18,000 pi. There are no units left in the top, so I'm going to use my placeholder again, radians per minute. And while that's the angular velocity measured in radians per minute, most of the world uses the RPM, revolutions per minute, so I'm going to go ahead and multiply that by one final conversion factor times, I need radians to disappear, so this time it's going in the bottom. I need revolutions to up here, I know that 1 revolution is 2 pi radians, and I get a final angular velocity in different units. Pi's cancel. 2 goes into 18,000, 9,000 times. And what's left are revolutions and radians in the top, so I'm just going to write revolutions and minutes in the bottom, which is the same thing as 9,000 RPM. So in a lot of ways this makes sense, because if one disk has a radius 3 times as large as the other one, in order to compensate, the first disk was spinning at 3,000 RPM. The second disk, which is smaller, is going to have to spin 3 times as fast to keep up, and that produces 9,000 RPM. So in one problem we can go back and forth between an angular velocity, a linear velocity, keep the 2 linear velocities the same, and convert that back to a second angular velocity. So that's it. Basically what we needed to learn was that angular speed uses omega as a variable. It's change in angle over change in time. Linear speed uses v as a variable and is change in distance over change in time, but sometimes a distance on a circle is called an arc length, so you might also see change in s over change in time. And the two can be related, because if I just take the linear speed, I can multiply a radius times the angular speed and wind up with the linear speed. So as long as you know these 3 formulas and a little bit about how to convert RPMs into radians per minute using the conversion factor, 1 revolution is the same thing as 2 pi radians, you'll know everything you need to know about angular and linear speeds.